So let's have a closer look at Lenz's law, because it's a bit of an unusual law, to be honest, and well worth a bit of investigation to understand. Well, remember what it is. Lenz's law says that the induced EMF is such as to oppose the flux change creating it. It was a bit mysterious. Or we sort of, the mathematical version of that was that it's the minus sign in Faraday's law, or what's actually called Faraday and Lenz's law, because of the minus sign. So Lenz's bit is the minus sign. So there's that law there. Okay, so what's going on? Well, a good example, a classic example for looking at this, is the example of a magnet. You kind of release a bar magnet and let it fall through a coil. So like before, we've just got a coil with an ammeter, a galvanometer. So if an EMF is induced, then the galvanometer will register. And of course, Faraday's law tells us that an EMF will be induced in the coil. We can see that's true because, I mean, there's going to be flux change. There's going to be a flux lines. These field lines are going to sort of increase. The flux linkage in the coil is going to increase. So we know, N phi is going to increase. It's going to be, as it falls, it's going to be an induced EMF. But the big question is, in which direction? In which direction is this EMF going to occur? And how do we decide? Well, there's obviously two possibilities. It could go kind of that way round, and therefore the current would flow that way round, or the other way. It could be that way round, and the current could flow. So the EMF is in the opposite direction to make the current flow the other way round. So those are the two possibilities. Looking down on the coil, we could either have a clockwise EMF and a clockwise current, or an anti-clockwise EMF and an anti-clockwise current. So which one's it going to be, is the big question here. Well, let's look at the implications of both and decide then which must be the correct possibility. So let's start with clockwise, means current going clockwise round, EMF clockwise, current going clockwise. So if the current arises that way, well, we actually have a rule, and we know what that means for this coil. We know that the direction of the field lines associated with that, and we can use the grip rule. If you remember the grip rule, well, the grip rule, remember, you align your fingers along the direction of the current, and then your thumb points to the North Pole. So hopefully you can see that the North Pole is going to end up here, and the South Pole at the top. If not, go back and have a look at the grip rule and where that all came from in the first, one of the first two videos of this course. So look, let's take away the arrows. Well, of course, we can see straight away that that would mean that this magnet is going to feel an attraction towards the top of the coil. And now, is that okay? Well, why not? Well, it's not okay because it would accelerate faster than g. So we've got a kind of major problem in physics terms, because if suddenly this has got no power supply, there's no energy coming from anywhere here, so it's just a piece of metal and an ammeter, and we're saying that if we drop a magnet towards it, if the induced EMF turned out to be clockwise, looking down from above, then it's going to start accelerating the magnet faster than g. Well, there's something wrong with that, isn't there? It breaks energy conservation. The reason it breaks any energy conservation is that when you drop something normally, well, it gets its kinetic energy from the gravitational potential energy that's converted. But of course, if it falls faster than g, then there's extra kinetic energy coming from, which must come from somewhere else, but there's nowhere for it to come from. So this is quite an interesting fact that Lenz realised. So that can't happen. Let's look at the other possibility then, which is the possibility of the EMF arising in the other direction, and therefore anti-clockwise looking down from above, like this. Well, we can use the grip rule again, and this time we know that the top will become a North Pole and the bottom will become a South Pole. Aha! Well, this time it's going to kind of repel the magnet. Now, why is that okay when it wasn't okay to attract it? Well, that's going to slow down the magnet, which means that some of that kinetic energy of the magnet is going somewhere, well, it goes into the electrical energy in the coil. So this kind of works. This is okay in terms of what's allowed by the laws of physics, yes? Because instead of speeding up and getting energy from nowhere, what we're doing is slowing down the magnet and allowing some of that kinetic energy, ultimately coming from the gravitational potential energy source that was available, and it'll turn into electrical energy inside the coil. So this is allowed under energy conservation. So this is pretty important. So basically, that's what Lenz's law is actually really a statement of energy conservation. But let's just see in terms of flux change what that means. Well, of course, if we think back right to when we started defining flux, you'll remember that we defined flux as the field multiplied by the area. So in this case, we're going to talk about the flux linkage. That's the flux linkage due to this magnet at any one moment. The flux linkage is the flux that passes through the coil multiplied by the number of turns. But you might remember, or hopefully remember, that we associated a direction with area. Pretty weird, but we did. So we said, well, we have the normal to the area, and if that's in line with the flux that's passing through the coil, then we say the flux linkage is positive. So the normal to the area in this case is we can choose. I'm going to say it's down, just because that's the same direction as the flux. And the flux due to the bar magnet at any one moment is also, because that's a north pole, is coming down in the same direction as the normal to the area that I've chosen. So that means that the flux linkage is positive. I mean, if I turned the area around, I could say it's negative. It doesn't matter, you'll see in a minute. So let's say here that at this stage, the flux linkage n phi is positive. And you know my shorthand for positive there. Okay, well, then what we've got to realise is that as the magnet gets nearer, that flux linkage is increasing. So n phi is increasing, yes, because the flux density gets stronger as the magnet approaches. As it falls down towards the coil, I mean, it's going to change when it goes through the other side, but we're not going to worry about that yet. And so that means that delta n phi is also positive, or we ought to say d n phi. The change in flux linkage is positive because it's getting bigger. Now, Lenz's law says that the induced EMF must oppose the flux change. So, well, now we see how this links to this business of the energy conservation. We've got the induced EMF has to try and stop that increase in flux. It's not going to succeed, but it has to make an effort to stop that increase. It's got to oppose the flux change creating it. The flux change creating it is an increase in flux. Yeah, the flux is starting small and getting bigger and bigger and bigger in a positive direction, what we've defined as the positive direction. So, so whatever arises in the coil just has to oppose that. So let's have a look. Well, here's if I just draw a quick version of that coil as just one loop. Well, if it becomes north at the top and south at the bottom, well, then we know that the flux is in a kind of upward direction. And so, well, now we can see, that is going to slightly cancel out this increasing positive flux, because this is a negative flux. So it's got to produce a negative flux linkage. Whatever EMF arises, whatever current arises, has to produce a negative flux linkage to try and cancel out the positive flux linkage. Because if the opposite happened, then it would add to the flux linkage, but we've seen that would break energy conservation, so it's not allowed. So that's what happens. So what we say is this. We say, well, the induced EMF must oppose the flux change by trying to reduce the flux linkage. And so, in other words, whatever EMF arises must create a current which creates a flux linkage in the opposite direction. and that will partially cancel out the flux, the growing flux linkage. It's going to try and stop that happening. And so that's why it has to be a minus. This is a negative flux change because the area is down. Yes, the area is downwards, but the magnetic field arising because of the new current is upwards. So that's a small minus, it's a small negative flux linkage. And so that's why we've got the minus there. Make sense? Hopefully so. Well, that's kind of quite a tricky thing. That's probably a video to watch again and think about. But we are going to work through a bunch of questions which will help us understand this even more.